Hello everyone. So in today's lesson I would like to continue studying linear transformations, and exactly in this lesson we will study kernel and image for linear transformations. So kernel is written there. It's if we have linear transformation from space V to space W, then we can say that our kernel is equal to this set. Look, these brackets are they are representing the set. So as you can see, from any vector x from space V, where this is set builder notation from discrete math we studied on previous lessons. Once again, the vector x from space V, where phi of vector x, that means this is transformation of this vector, is equal to 0. So this is all vectors from V when after transforming them they are equal to 0 in our space W. So I hope it's clear for you. So let's now move on and solve exercise number 2. Let a linear transformation phi from R5 to R3 be defined as. Look, this is our transformation named phi. So from this vector we transformed into this one. This is some matrix multiplied by this vector which was at the beginning. For any vector, this is no, you can it is a row, and this is mean that it is a column, you know. This vector belongs to R5. Then find the basis for kernel phi. Yeah, here we also have basis. So let's find. We already know what this kernel is. And now let's see. It's all vectors from V where our transformation our output is equal to 0, and this is our matrix multiplied by some vector, and this is our final product. It's our output. We have input, we have output. So a linear transformation is a function. To more brief explanation of linear transformation, I really recommend you to watch the video from channel 3 blue 1 brown. It's a really good video. So yeah, our final product is equal to 0, so we have easy equation. So let's solve it. Yeah, and it's just linear equations, system of linear equations. So yeah, we are going to apply reduced row echelon form to find all axes. So yeah, this is REF, and as you can see, we have two leading elements. This is one leading element and this is two leading, so all dependent elements, this one, and also this one, we denote as some A, B, and C. And x1, x3 is just, no, as you can see there, we just move from another side. I think it's easy, and we can also write it like this, that this matrix is equal to this one. As you can see, for example, the third expression, we have a0 there and 1b and minus 3c, and if we count this, we will get the same thing. So yeah, so kernel of v, it is set of these vectors. Yeah, we found it. So that is it. It depends on what A, B, and C we get, we input, because we don't have some exact vector. We have some just x, you know, and so this is depends on this vector. So if we have some x's, then we need corresponding A, B, and C for this. So kernel is equal to this one, the set of three vectors. And in this exercise, we ask to find the basis of kernel. So let's write it as a matrix and see how much linear independent vectors do we have. We write these three vectors as one whole matrix and apply reduced row echelon form. And as you can see, there we have all linear independent vectors in this matrix. So that means that every column, every vector from each column is also linearly independent, and that means that our basis is the same as our kernel of transformation phi. So okay, and also we need to find the basis for image, and image is just all vectors from output. We have input, we have output, and image it's basically all from output. So yeah, we already know that RREF of this matrix is this one, and yeah, so basis of image is independent vectors. So yeah, this is our image. Okay, let's move on and solve exercise 3. Does there exist a linear transformation phi from V to W such that, as you can see, there we have it is our first space and this is our second space. This is V, this is W, V, W, V, W. And it's all from R3, three-dimensional space. Okay, and we need to find if there exists a linear transformation. So we have three linear transformations, and what is actually this transformation? We have some vector, and when we do some operation with this vector, we got output new vector. So that means that we can write a multiplied by this vector, we got this vector, and we write it for all three transformations. So now from this system we can subtract one matrix, and the matrix of input and the matrix of output, and write this equation. So we can call this matrix of vectors of input as B, and then say how to find A. A is equal to this matrix multiplied by inverse B, B in the power of -1. So let's find B into the power of -1 inverse matrix, and we do some arrow there, elementary row operations, and finally we got that this is our inverse matrix. And so we multiplied it, and yes, this linear transformation exists, because we can see that this is our matrix. If we put it in every case, or exactly in this, because this is not a whole matrix, then we will get this one. And as you can see, A in the size of 3 by 3, and this is 3 by 3, and this is 3 by 3. So then we can say that we can multiply these matrices and nothing will go wrong. Okay, so I think it's clear. So linear transformation exists. Now let's check one more example, the last one. We have, as you can see, V, which from R3, and W from R2. So we also got three transformations. We do the same thing. We construct matrix of inputs and from outputs. And let's see. A is, as in the previous exercise, A is equal to this one. So, and this is mistake, because I mean, so we cannot find B minus 1. We need to find some A which can which we need, and we can find it because if we try to find inverse matrix, then we will see this, that the determinant is equal to 0, so there is no exist b in the power of -1. And we found determinant by using Saros rule. Yeah, I think it's the easiest easiest way to do this in this case. So there is no exist b minus 1. That means that we cannot find some matrix A, and so that means that linear transformation does not exist. It does not exist. I forgot S there. So yeah, I think these exercises are not really complicated for you, and you understand it full. So thank you for watching, like and subscribe for my channel, and see you in the next videos.